evolution involves huge dramatic changes like the creation of a whole new species. But actually, evolution can happen on a very small scale, and this is known as microevolution. In this video, we're going to take a look at some of the main components of microevolution, as well as the opposite of microevolution. So let's start off with a better definition of microevolution. In this population of butterflies, we could calculate the frequency of both the dominant and the recessive alleles. And if we looked and counted, we would see that there's one recessive allele out of a total of 8 alleles in the gene pool. And if we use the letter Q to represent the frequency of the recessive allele, we would see that there's a 12% frequency of that lowercase t. Meanwhile, if we use P to represent the frequency of the dominant allele, 7 out of the 8 alleles are dominant, and we have a frequency of 88%. But what happens if in the next generation we get this? So here is a different population of butterflies, the offspring of this population, and if we count up the recessive and dominant alleles and calculate frequencies, this time we see that there are 2 out of 8 alleles in the gene pool that are recessive, giving us a frequency of 25%. Likewise, only 6 out of the 8 alleles in the gene pool are dominant, giving us a 75% frequency. Because there has been a small change in allele frequency from one generation to the next, this is known as microevolution. So keep in mind a couple of things. All that we needed to change was the frequency of alleles, and this change happened from one population to the next population. It didn't happen in individuals. So let's say we wanted to observe microevolution in the real world. Well, we have a slight problem. In the example we just looked at, I had butterflies with their alleles basically printed on their backs. But in the real world, organisms don't run around or fly around with their alleles stamped to them. So the only thing we can observe in the real world is the phenotypes. But we can get one important piece of information from observing the phenotypes of a population. If we know, for example, that the brown phenotype is recessive, then we do know what that genotype is. We know that this organism must have 2 small or recessive alleles. And that's going to provide a starting point for calculating the frequencies of alleles in multiple generations. So to do that, we're going to use the Hardy-Weinberg equation. And I'm going to explain how to use this equation using a case study of the blue-footed boobies. So in our blue-footed booby population, we're going to focus on one particular trait, the feet. Webbing is the recessive trait, no webbing is the dominant trait. So let's say we have 2 boobies who are in love. They're both heterozygote for their non-webbed feet. Now, if we were to predict using a Punnett square what their offspring will be, we'd set it up like this. Both parents have a 50% chance of contributing either the dominant allele or the recessive allele. If we put that in a Punnett square, we would see that there's a 1 in 4 chance of a homozygous dominant baby booby, a 2 in 4 chance of a heterozygous baby booby, and then a 1 in 4 chance of a recessive baby booby. Now, we're going to set up the same Punnett square, but we're going to substitute some different variables. And one thing to keep in mind, that if we add up all these frequencies, we're going to get 1. The total probability of each component of the Punnett square adds up to 1. But let's do it again, and this time, instead of having 1/2 W be our probability, we're going to substitute the letters P and Q. Remember that P is the frequency of the dominant allele, and Q is the frequency of the recessive allele. So these P's and Q's actually represent numbers. So if we fill in our Punnett square this time, the chance of homozygous dominant is P squared. The chance of heterozygous dominant is PQ plus PQ, which is really 2PQ. And then the chance of heterozygous recessive is Q squared. So this is where our equation comes from. P squared plus 2PQ plus Q squared equals 1. It's really just a simple Punnett square, but we're substituting p's and q's instead of probabilities. So let's apply this equation. Remember that p squared is the homozygous dominant genotype, 2pq is the heterozygous dominant genotype, and homozygous recessive genotype is q squared. The tricky thing about using this equation is to remember that individuals with the dominant phenotype are represented by p squared plus 2pq, because there are two ways to get the dominant phenotype. You can be homozygous dominant or heterozygous dominant. Another important thing to remember is that p and q, our two frequencies, always have to add up to 1. So if you use these equations together, you can calculate the frequencies in any population. So here's an example. If we had a population of 500 boobies, and if we knew that 20 out of 480 had the dominant phenotype, we would also know, therefore, that 480 had the dominant phenotype. So we can start there with 20 out of 500 and calculate q squared, and that would give us 0.04. Once we know q squared being 0.04, we can calculate q by taking the square root, so we get 0.2. Once we know q, we can find p. Since p plus q have to add up to 1, if q is 0.2, then p is 0.8. Finally, if p is 0.8, p squared must be 0.64. And then we can simply multiply those frequencies by the total number in the population, 500, and we would get the actual number of individuals. So a good rule of thumb is to always try to get either q or q squared. If you can figure out q or q squared, the rest is easy. So under what conditions can we use this equation? Well, only when the population is at equilibrium. In other words, it is not evolving. So there's a website that does a nice job of outlining the conditions needed to keep a population at equilibrium. Let's take a look at that website. So in this case, we have a population in equilibrium. The frequencies of the different alleles are not changing. But there are certain conditions that will upset equilibrium. One of these is non-random mating. In this case, the purple are seeking mates within the population. They are able to reproduce more successfully, so the frequency changes over time. No equilibrium. Another condition is migration. Here's our original population. If certain individuals leave, that's going to change the frequency. Again, no equilibrium, evolution instead. Another factor that will disrupt equilibrium is genetic drift. In this case, we've got some chance events that affect these genotypes. And as a result, again, no equilibrium, evolution instead. Mutation, which we're familiar with. If a few of the alleles actually mutate and become a different allele, again, we will change the frequency. We will have evolution, not equilibrium. And the only force that will lead to adaptive evolution is natural selection. For some reason, this is not an adaptive trait, so it becomes weeded out of the gene pool, and we have evolution. So one more time, to keep things in equilibrium, we need to make sure that there's random mating, no migration, no genetic drift, no mutation, and no natural selection. Here they are. And I'm just going to review these one more time because it's super important. Genetic drift tends to happen in a small population, will lead to evolution. In this case, a few people moved away to a new area. Their gene frequencies weren't the same as the original population, and as a result, we have evolution. Keep in mind that this isn't adaptive, though. It doesn't necessarily make the population better, it just makes it different. Another type of genetic drift can be a bottleneck event where some sort of natural catastrophe destroys much of the population. Again, not necessarily adaptive evolution, just randomly destroys many of the genotypes. Here we have non-random mating, where beetles of a certain size like partners of a certain size. This is just a form of sexual selection, and it will also lead to evolution. Gene flow, aka migration, where individuals leave or enter a population, will lead to evolution. Here's another example of gene flow. This is happening as pollen from one population of trees migrates to another population of trees, changing the genotypes and the gene pool. And our adaptive form of evolution is natural selection. If there is a selecting agent in the environment that allows one phenotype to survive and reproduce more than others, you will have a change in the gene pool. More organisms in the population will have that favorable phenotype, and evolution will occur. So let's just quickly review the basics of natural selection using bacteria, which is one of the most common examples currently happening today. So here we've got a bacteria population, and as you can see, there's variation. These are the normal strains, but then we have a few mutant bacteria that actually have resistance to antibiotic. So if there is a change in the environment, if we apply antibiotic, that acts as a selecting agent. It selects for the mutant phenotypes and selects against the normal phenotypes. So now, these mutant phenotypes actually have an adaptation. The mutant phenotypes survive because they are more fit. The non-mutant phenotypes die because they are less fit. And over time, more and more of the population comes to have the mutant phenotype because they are able to reproduce more successfully, and thus the population changes. Keep in mind that the variation was present initially in the population. It didn't occur in response to the environment. Also keep in mind again that evolution happened in the population of bacteria, not to an individual bacteria. So there's a few types of natural selection. One is stabilizing selection, and this happens when the intermediate phenotype, the in-between phenotype, is favored over time. So here you can see the original distribution of phenotypes in the population, and over time, even more of the population is getting the intermediate phenotype. And this tends to happen when you're in a stable environment that favors the intermediate phenotype. A second type of selection is directional selection, which is exactly what it sounds like. Here's our original population with a range of phenotypes, many of them in the intermediate, but with directional, what happens is the environment changes in favor of one or the other phenotypes, and so the population changes as well. Here you can see that over time, more and more of these mice are coming to have the darker phenotype because that's favored or selected for in their environment. And the last main type of natural selection is disruptive, also known as diversifying selection. And this happens in a patchy environment where you've got a couple of extremes. And what happens is that both extreme phenotypes end up being favored. So the original population, the intermediates were favored, but because of this patchy environment, both the light extreme and the dark extreme become favored. And just a quick review of sexual selection, which is also known as non-random mating. This occurs when mates act as the selecting agent. In this case, we can see that females are preferring males with the big purple spots. So over time, the population changes and more of the males have big purple spots. And that is the end of our video on microevolution. If you didn't take notes, please make sure you go back and take notes and that you've got the 5 conditions for equilibrium straight, and you can list them from memory.